So the plan is to discuss what is called continuity theorem. Yeah, continuity theorem. So it is just the connection between characteristic function and convergence with distribution. I think I defined convergence with distribution in the last class. I will recall it again. Okay. So we have already defined some convergence of random variables, some definition of convergence of random variable. So one is, of course, we have a random variable, collection of random variable, xn, such that xn converges to x almost surely. That is xn, we denote it like this. Huh? No, there was no discrete case about that, which was the definition is general. Okay, probability or whatever, the definition is general. Okay. We didn't assume anything discrete. While discussing, there was no discrete in that, right? Even the proof, it used some inequality. That is, I mean, when that expectation satisfies that inequality, expectation satisfies that whatever the expectation is positive, x is less than y, ex is less than ey. These kind of things we proved for continuous case also. So when they satisfy that, they satisfy the Markov inequality or whatever, Chebyshev inequality, law of large number, whatever we prove, we will prove another law of large number, bit more general. We won't assume the expectation. I mean, the second moment exists or something we assume. We will not assume that now. So without that, we will prove weak law of large number. Okay. So this is general. If this means that there exists a set A, I mean, you need to, for this, you need to refer to the probability space. There exists a set A contained in omega such that probability of A equals 0 and xn of omega converges to x of omega for all omega in A complex. Okay. Only a set of probability 1, the convergence happens. This is what almost surely convergence. Okay. 2, we say that xn converges in probability to x. Here we need not refer to only the probabilities are needed. Okay. This has to refer to the probability space. Here the probability space is not needed. It can be in the background. Of course, always it is there in the background. These are all defined on the same probability space. Xn converges to x if probability of all those omega such that this happens. Xn minus x greater than epsilon goes to 0 for all epsilon greater than 0. Okay. This is convergence in probability. These two are actual very nice convergence in the sense that if something converges almost surely, then the limit is determined almost surely up to probability 1. I mean, if there are two limits, they are same. The x of omega equal to y of omega and a set of probability 1. If xn converges to x, xn converges to y, then x omega equal to y omega for omega in some set of probability 1. So this limit is unique in that sense. Here also the limit is unique. We proved that. So here third one, the limit as a random variable, it's not unique, but the distribution is unique. Okay. This is convergence in distribution. We say this is something vague. Xn converges to x in distribution. This means that fxn x converges to fxn x converges to fxx. This is the distribution function of that. Okay. This is for both discrete and maybe combination, all that. Okay. For all x in R such that f is continuous, fx is continuous at x. At all continuous points of this distribution of x, this convergence happens. Okay. So when when we consider continuous variable, the convergence happens at all points. Okay. There is no difference. So we will come to this later, maybe, may not be, but we will discuss these two. So this is the proposition. Xn converges to x in probability, then Xn converges to x in distribution. Okay. Convergence in probability implies convergence in distribution. The other way is not true. We'll give a counter example. Okay. Well, remark. Let's first prove the remark. Xn converges to x in distribution. Of course, see, distribution has nothing to do with the probability space, right? I mean, it is just the distribution function converges to something. So you can see that it can, if xn converges, it does not imply xn converges to xn probability. Okay. Example, you take xn IID. Okay. Then they all have the same distribution. Okay. And with distribution f, with distribution f. Okay. And x be anything with f, any random variable with f. Then xn converges to f, of course, distribution. Okay. And there are many random variables with the same distribution, of course. It means it all converges to that, right? So this is something vague. Okay. If xn is an IID sequence, the independent, and so they are all okay, then this can happen. Okay. So you can take Bernoulli, for example. Xn's are Bernoulli sequence. Xn converges to x. Then 1 minus x, that is also Bernoulli with half. Okay. Probability equal to half. Then x and 1 minus x both have the same distribution. So it will converge to, xn will converge to x, xn will converge to 1 minus x also. They are not equal, of course. Okay. So this is not, then, I mean, but the probability, the limit is unique. Here the limit is not unique. So, I mean, limit as a the random variable should be unique. Limiting random variable. In probability, convergence in probability, the limit is unique, determined almost surely. So here it's not determined almost surely. That itself shows that if something converges in distribution, need not converge something in probability. So the proof of this. So xn converges in probability, then we want to prove that xn converges in distribution. Proof. Okay, this. Okay. So we want to prove it converges in distribution means fnx, whatever the distribution of we want to prove, we have probability of xn minus x greater than or equal to epsilon, whatever. Proposition, of course, proof of the proposition. That was a remark within brackets. It's an easy remark. So suppose we have convergence in probability, we have this, and we want to prove the distribution fxn at x converges to fxx for all continuous points of f. Okay. That is probability of xn less than or equal to x converges to probability of x less than or equal to x for all continuous points of f, wherever that is continuous. Okay. Continuous means probability of x less than or equal to x is same as probability of x less than or equal to x. That's what continuous point means. Okay. I mean, if it is not continuous, there may be a jump there. Continuous is equivalent to saying probability of x less than equal to x equal to probability of x less than or equal to x. This is the continuity of f. Okay. Okay. Continuous points of fx. Yeah, you are right. Okay. Okay. So let's epsilon greater than, we have to deal with epsilon, of course. Epsilon greater than 0. Then we consider this probability of xn less than or equal to x. Okay. This is equal to probability of xn less than or equal to x and x less than or equal to x plus epsilon. Probability, I mean, this set is equal to this set intersection omega. So you can take some a complement, any a and any a complement. So that a is this set, x less than or equal to some property determined by some property, which is xn less than or equal to x, x less than or equal to x plus epsilon. Similarly, xn less than or equal to x and x greater than x plus x. Okay. Okay. These two are equal, right? Any set probability of B equal to probability of B intersection A plus probability of B intersection A complement. Okay, for any A, and our A is this property determined by this property. Okay, this set. Okay. This is right. Okay, that's all. So now this set, of course, you remove this condition, that will be a bigger set only. So this is less than or equal to probability of x less than or equal to x plus epsilon plus probability. So x, sorry, this is xn, capital Xn. Capital Xn is less than x, capital X is less than x plus epsilon. So the difference will be greater than epsilon. Okay, so this is probability of this is less than this. Of course, you can take the mod less than or equal to. I'm only taking okay, this line. This line. I wrote it here now. Probability of any set B is same as probability of B intersection A plus probability of B intersection A complement for any A. Take that set A is equal to all those x less than or equal to x plus epsilon. Okay. This intersection, this intersection, the complement. That's all. Okay. Now this is true. So this, I have removed this condition. That will be a bigger set. Will have bigger probability. Okay. So P of A is contained in B. P of A is less than or equal to P of B. I'm using that monotonicity. Similarly, this is also a bigger set. I'm taking mod and this set. This implies that condition. So this is okay. Okay. So this is one. The another way, if you have P of x less than or equal to x minus epsilon. Okay. The same way, you do the same argument. I mean, you take Px less than or equal to epsilon. Okay, if you want Px less than or equal to x minus epsilon, and xn less than or equal to, for some n, of course. N is arbitrary but fixed n. Xn less than or equal to x plus P of x less than or equal to x minus epsilon and xn greater than x. Okay. So similarly, this is less than or equal to P of xn less than or equal to x plus again P of xn minus x greater than epsilon. Huh? Absolute value of what? I want to keep the xn inside and write the inequality. I want to compute this limit, right? This is the fxn. This is what I want to compute. I want to keep this within some inequality and that both will converge to the same limit. That's the idea. Okay, right? So I want to keep this in the middle of the inequality. So this says that probability of xn less than or equal to x, I can bring this here. So probability of x less than x minus epsilon plus probability of mod xn minus x greater than epsilon. Okay. Whatever. I have just brought it here. That is less, this is less than or equal to probability of xn less than epsilon, less than or equal to epsilon. Okay. Now this is there I have less than this inequality, probability of x less than x plus epsilon, okay, plus probability of again xn minus x greater than or equal to epsilon. This is true for all epsilon, for all n. Okay. Okay. Now we know this goes to 0, fixed epsilon, this goes to 0. Okay. This goes to 0. Possibly there's a minus here. Sorry. This is minus. This is minus. I have brought it that side. So this 2 goes to 0. So if you take the lim inf, okay, here the lim inf is taking a same as taking lim sup. Sorry, lim inf is taking a same as taking limit. Okay. Similarly, this is that is also because limit exists for that. So you can take lim sup or lim inf. Okay, this will go to 0. This will go to 0. So we have the following inequality, which I write it here. Take lim min for lim sup, whatever. Lim min and lim sup, both. Okay, but lim inf of. So this implies lim inf of fxn at x, okay, is less than or equal to f of x plus epsilon. Okay. And similarly, I mean, lim inf is of course less than lim sup. Okay. X and x, which is always true. You can take lim sup or lim inf, both will stay in the middle. That is less than f of x plus epsilon. Okay. This is greater than f of x minus epsilon. Okay. So suppose x, f is I mean, here it should be f, of course. F. Okay. Suppose f is continuous, fx is continuous at x. Okay. Then limit epsilon going to 0, fx of x minus epsilon is equal to limit epsilon going to 0, f of x plus epsilon. Okay. Of course, equal to f of x. Okay. So then these two should be equal. These two should also be equal. Okay. These things implies that limit of f x and x is equal to f of x for at a continuous point. Then we had some inequality. This one, that is just the definition, no? Pf, that is just x less than or equal to epsilon is this. Xn less than or equal to this is that exactly. So I used probability so that we can write those inequalities. Then that is precisely equal to this. Okay, so by taking limits, we got this. Okay, so convergence in probability implies convergence in distribution. Okay. So there is a counter example. I don't remember. So for this, it's not important. We will, but it's clear that it's not true. So xn, or if you take just fn, some distribution function, fn's are distribution function, can just f. Okay, then distribution function, okay, or fn, f for distribution. Okay? I mean, we can write it like this also. We need not consider random variables. We just consider just a distribution function which converges to this pointwise. I assume that they are continuous random variable also. Okay, does not imply fn converges to f, where fn, f are densities, corresponding densities. Okay? Okay. If fn, capital Fn has small fn as density, capital F has, this need not happen. Okay, there is a there are many counter examples. I don't want to get into that. But the point I want to tell you is, see, integration is like a continuous operator. So if fn converges to f under some nice condition, suppose if it is uniform convergence or some nice convergence, not point-wise convergence, then integral fn will converge to integral f. But if we differentiate, that will not happen. Differentiation is not a continuous operation. Okay? If fn converges to f, then the derivative need not converge. Okay, so that is what that is the remark. Okay, okay, but the following is true. Okay, let fn. I mean, I can write random variables and state it, but I'm directly, there is no point in that. So fn, f for distribution function. Okay, we can just directly straight away deal with distribution. Fn, f for distribution function with densities fn and f respectively. Okay. Then if I mean, there is some alphas. Let's deal with point-wise convergence. Fnx converges to f of x for all x. Then then the other way is not true. And there is continuous distribution, point-wise convergence. Okay. So if the distribution function converges point-wise, does not mean that densities will converge. But if the densities converges point-wise, then the distribution function will converge. Okay. So that is the theorem. So proof. I mean, we want to prove the following. Want to prove minus infinity to x, fn x, which is what is fn x, which is what equal to fn x, right? Converges to minus infinity to x, f of x. Okay. Okay. This is what is f of x. Okay. This is what we want to prove this. Okay. So that is, we want to prove the modulus of the difference between them equal to 0. So modulus of minus infinity to x fn minus f is less than or equal to minus infinity to x mod of fn minus f, okay, which is less than or equal to minus infinity. This is positive, so minus infinity to minus infinity mod fn minus f. So it's enough to prove this goes to 0. Okay. This is modulus, you can take it inside, and then this is a bigger, and it's positive, and so it's important it should be positive. The area will be bigger. Okay, integration is just the area, so the area will be bigger. So this is this. Okay, if you want, you could dx, whatever. Now I want to prove this goes to, it's enough to prove this goes to 0. Okay. Now we have the following: integral fn dx equal to integral f dx. Okay, that is integral fn minus f. I mean, both are equal to 1, right? All are equal to 1. That's what I'm using. Integral fn equal to 1, integral f dx equal to 1 for all n. Okay, for all n. Okay, so this is equal to 0. So the positive part, when you integrate the positive part, negative part, both are 0. So integral fn minus f minus fn plus is equal to integral m minus infinity to infinity. Okay. I mean, we are taking on the whole real line, minus infinity to infinity, f minus fn minus. You remember this positive part of a function, negative part of a function I defined some time back, which is just the maximum of, I mean, if you have any function, g, okay, g plus is equal to maximum of g of x and 0. Similarly, g minus equal to maximum of 0 minus g of x. Okay. When g is positive, this is non-zero, and g is negative, this is non-zero. Both are positive function, and any g is equal to g plus minus g minus. Okay, and mod g is equal to g plus g minus. We proved, we discussed all these things before. Okay, so integral fn minus f is equal to 0. Okay, because they are equal, so integral fn minus f is equal to 0. So the integral fn minus f is this minus this, fn minus plus, fn minus minus. Okay, the integral is linear, so these two are equal. So this implies integral minus infinity to infinity mod fn minus f, okay, is equal to 2 times integral minus infinity to infinity fn minus f minus fn plus plus. Okay. Okay. Mod of this is f minus fn plus f minus fn minus. Okay, both are equal, so this is just 2 times that. Okay. Okay. Now f minus fn, this goes to pointwise to 0. At each point, fn is going to f. Okay. On the other hand, f minus fn plus, okay, is less, fn is positive. Okay, it can't go, fn is positive. These are all positive function. So fn cannot, I mean, fn is positive. So f minus fn is non-zero only when f is less than, sorry, fn is less than f. So this is in particular less than f of x. f1 minus x at x is less than or equal to f of x. Okay, for all n. And integral f is equal to 1, right? So this is bounded by a function which is an integrable function. Okay, so you can take the limit inside, and the limit goes to 0 inside. Okay, so limit n going to infinity, integral mod f minus fn minus infinity to infinity equal to integral minus infinity to infinity limit n going to infinity f minus fn plus 2 times that equal to 0. Okay, so this goes to 0. That's what we wanted to prove. Okay, so that's true. We wanted to prove this, which is equivalent to proving this. Okay, and we are using the dominated convergence theorem. Okay, whatever the sequence or whatever you can insert a parameter or something, it's all uniformly bounded by an integrable function in that parameter. Here the parameter is n. This is for each n we have something here. These are all dominated by one single f. Okay? F minus fn plus is less than or equal to this. Okay? And this is an integrable function. So you can take the limit inside. When you take the limit inside, that becomes 0. Okay? That's all. So we have proved it. Okay? If densities converge, so probability convergence implies distribution convergence. Density converges, then also the convergence in distribution happens. Okay. Okay. So let's go. We want to prove the following theorem. Maybe I need another lemma. Okay, let's do that. We have already done that, but we have done for density which are continuous. Okay, this is the theorem. Continuity theorem. Okay. We will prove one way, the other way is also true. Okay. We want to prove the density. Okay, let xn's are random variables. Xn converges to, no, not xn is xn's random variable, x sequence of random variable has distribution phi, phi n. Okay, I may forget phi xn or something, so I call it phi n. Okay, and x is a random variable. These are random variables with distribution phi. Okay, suppose then xn converges to x in distribution is equivalent to saying phi n converges to phi n of t converges to phi of t for all t. Okay. Okay. The characteristic function converges pointwise, which is equivalent to saying the random variable, original random variable converges in distribution. You can directly consider distribution function, but for some reason we want to consider random variables. Okay, because we want to add something and do something. Okay. Proof. And given any collection of distribution, see, we haven't proved the existence of distribution, I mean, random variable with uniform distribution. We haven't proved. I mean, we didn't prove rigorously. Suppose Z exists, then any random variable exists with any distribution that we proved in the class, if you remember. You can just take the, I mean, if provided it is continuous, you can use the transform using this F inverse, if you remember in one class we proved. If X has uniform distribution, okay, and F inverse X has distribution F, okay, this we prove. Okay. I mean, if it is continuous, F inverse exists. I mean, if the distribution function is continuous, F inverse exists. It will be strictly increasing, so it will exist. So we have proved this. Okay. Any discrete random variable, you can always directly get a probability space and other things. So here, if we can get it for uniform distribution, if some uniform distribution, given any uniform distribution, you have a random variable with that uniform distribution. Huh? This is characteristic function. What? Oh, this is characteristic function. Sorry. I'm sorry. That's what I said, right? I did say some two. No, I said characteristic function is equivalent to convergent distribution, but I didn't write. Okay. This with characteristic function. Sorry. Okay. With characteristic. Sorry. This is with characteristic function. I mean, distribution, it is same, no? There is nothing. It's the same statement. There is nothing in that, right? I did say characteristic function converges if and only if the convergence happens in distribution. Okay. So, yeah. Whatever I wrote that's trivial. That's the same thing. Okay. So if it converges, the characteristic function converges pointwise. This is characteristic function. Then random variable converges in distribution. What I want to say is, given any collection of distribution, finitely many, we can always construct a probability space where that with random variables with the distribution. Infinitely many also you have to do, but that's more difficult. Okay. For finitely many, we have already discussed more or less, except the existence of uniform distribution. Anyway, that's not the point. So suppose if you have xn converges to, so we want to prove this. We want to prove this direction. Okay. Suppose we have random variables xn and x such that phi n converges to phi t. Okay, assume phi n converges to phi n t converges to phi of for all. Then we want to prove that xn, the distribution of xn converges to the distribution of x. Okay, that's what we want to prove. Okay, so let's define. So x k n, let z follows normal 0 1. Okay. We want to prove the xn's are random variables. They have characteristic function phi n, and x's random variable with characteristic function phi and t, the characteristic function pointwise converges. Then we want to prove the random variable converges in distribution. Okay, so we have xn and x. Now I define z is a normal random variable. I take a normal random variable. Okay, and we assume that they are all defined on the probabilities. As I said, as far as we only have to consider finitely many of them. So at finitely many, if they exist, that's fine. I mean, that is enough for us. So define xkn equal to xn plus 1 by k times z. Of course, k is in natural. Okay, here n is also a natural. It's a sequence. N is a natural number. K is a natural. So we have a double sequence. Okay, where I'm just adding that z, and we know that 1 by k z follows normal 0 1 by k square, right? It's normal, so it follows 1 by k square. Okay, so I have taken xkn. Okay. Now, from the given characteristic, we are given the characteristic function of xn, and normal, we know everything. From this, we can write the density of xkn, okay, the claim. 1 by k times z. Then, sorry, zk. Z 1 by k z, okay, which I call it zk is equal to 1 by k z. Okay. Okay, then I can put zk. Okay. This is okay. Okay. Zk is 1 by k z. So xn plus zk, which is xkn. Okay. This proof is not in Hoyle-Portstone, or I don't see in any other book also. Okay. I gleaned it in many places. Okay. The lemma, everything, whatever is needed, took it from many places. So you better you look at it. Okay. So if you don't understand anything, but it's very easy, as you can see, it's all very simple technique. This is 1 by k square. Normal 1 by k square. The claim is the density Fn F, if Fn F or density of xn xfk, right, xk, and this is, and is also, one more thing, we have this yk, x is already there, so better use yk, x plus zk. Okay. I'm adding zk, which is k times z, to xn and getting xkn, and I'm adding x plus zk to be yk. Okay. So if Fn density of Fnk, density of xkn, okay, and Fk density of yk, okay, then this is the claim. I mean, why it should be density? Because it can be discrete, but when you add with the normal variable, it will actually become continuous. Okay, the density is, claim is Fn kn at x is equal to integral 1 by 12 pi you can directly do it with our inverse formula. Okay, but then inverse formula, we assume that these are all continuous. Okay, so we can prove it also. Okay, with this, but because you have a normal thing, this proof is easy, very easy. In general, it will be difficult. Okay, fknx equal to 1 by 2 pi. Mm, right. So I need the characteristic function of that, which is phi n t. Okay, e power minus I t y. Okay, minus sigma square t square, which is sigma is this. So t square by 2k square. Okay, dt. X, where is x? X has to be somewhere. So I think it should be here. I mean, instead of t, wait. So then this should be y. Wait, we can, I think here only x. This is phi of t. 1 second, phi of t. This is t square and I, yeah. Now it's okay. To check this is correct, our zkn are and independent also, okay? And z is, I mean, we assume that z is independent of xn's and x, okay? I mean, I'm just, this is possible. If you don't get convinced, it's okay, but this is possible. If you have some sequence of random variable, you can have another random variable which is independent of all that. We only need up to finitely many, which you can construct product space and do that. Okay, so you have a product space where this happens, and we are actually worried about the distribution only. Okay, where that is defined does not matter. So they are independent. So xkn is equal to xn plus zk. Xn and zk are independent. So their characteristic function of this will be product of these two characteristic functions. They are independent. So that is what I have written inside. This is the characteristic function of xn. This is the characteristic function of zk. Normal. This is the normal one. Yeah, normal with mean 0, no? Yeah, no, this is just, I mean, this is not the characteristic function. This is the characteristic function. P square by 2k square dt. I mean, same thing I'm writing, but this ext is just the integration of the inverse formula. In the inverse formula, you have this, no? If you have a characteristic function, to get the density, you integrate with respect to e power ixt, right? Minus ixt. To get the characteristic function, you integrate with respect to plus ixt. To get the density from the characteristic function, you integrate with respect to this. Okay, so that is this term. This is the density of that. This is the density of this. Okay, and this term is always there, 1 by 2 pi. So from the inverse theorem, this is true. What we have done, it's true, except that we have proved it. Assumed that this is function is continuous in that. If you remember, we proved our inverse theorem for the density, not the distribution. The density is also a continuous function. That's what we assume. But here you can, but we can prove for this. I will prove it. Okay, and before that I will, and also fk. This is fk, no? Fk at x is equal to the same thing, except that there won't be any n. Okay, integral minus infinity t minus infinity to infinity phi of t e power minus ixt e power minus t square by 2k square dt. Okay, this is the claim. This follows if you assume the inverse theorem, but we have proved only for continuous function. This is in general, I want to say. Okay, let us just prove this claim. So this is just the proof of the claim. For general. As I said, if you use the inverse theorem, this is just clear, because this is the characteristic function of x and this is the characteristic function of zk, and the sum is the characteristic function is just the product of them. So when you invert it, you should get the density, okay, of the, but instead we will, but that since we approved only for continuous function, I'm proving it here. Okay, so the density fkx equal to, fkx is the density of xn plus zk, right? But we know the density of two independent random variable is convolution. Okay. So because of that, this is equal to minus infinity to infinity. Yeah, the convolution. So f of t dt, right? Let's say e power e power. I mean, if phi is the density of, we have used all symbols. So let's give me some symbol for normal distribution. Let f g be normal distribution. Okay? G is the density for normal 0, 1. Okay? G sigma, whatever, g 1 by k or whatever. Okay? G sigma is the normal distribution. Okay? G is the normal density of normal 0, e power minus x square 1 by square root 2 pi. Okay, whatever. Okay? G, G z. No, no, no. I want to use, this is just the notation for the normal one. I want to take the convolution of this and this. Okay. So if this has, okay. So you have this fkxt. I mean, I want to talk about fkt. Sorry, not fkt. What is this? fnt. Fn is the density of xn. Okay. Xn has a density, no? Xn has density Fn, okay, and X has density F. Okay, this is okay. Xn has density Fn. So this is just the convolution of Fn and the normal one, Zk, whatever. So Fnt, Zk is e power minus x square by, that will be x minus y square by 2k square, okay, dt. dt, right? No, no, wait. F of x, F1k, Fk, yeah, n, yeah, you are right. Fk n at x is equal to Fn at, here it should be y, no? Here it should be, maybe this is y, maybe x here, then y here, then this is y minus x or x minus y, doesn't matter. It's a square, so x minus, I want to put y minus x, but we will get x minus y is also okay. 2k square, then dy. Okay. Okay. Then there is a 1 guy square root of pi. Okay. Now, we have to use the property of the normal distribution to get this. That's all. Okay, which property we want to use? Normal density, the characteristic function, and the density. They are both they are more or less same. What expectation? No, expectation is. I mean, expectation is there. When you integrate, there is some expectation going on. Don't worry about it. We use the integration properties. Okay. So I'm saying that characteristic function of normal and that are same. I want this symbol so that I can write it here. Okay, G sigma will the G 1 by K normal 1 by K square. Okay. So, okay. Now this is nothing but 1 by square root of 2 pi minus infinity to infinity. This is nothing but so did I, there I get K square. I should get K square there, I think. No, no. Did I write K square? No, here it should be K square. See if you have a normal density, if something normal 0 infinity, 0 sigma, then the characteristic function e power sigma square by 2, no? Sigma square t square by 2. Not 1 by sigma comes in the density, it comes in the below. The characteristic function, it is sigma square. So it should be K square here. Sorry, this is a mistake. It should be K square here, right? Normal, the density is 1 by, normal, the density is 1 by square root of 2 pi e power minus assume mean is 0, t square x square by 2 sigma square. The characteristic function is sigma square in the top. Okay, that's the formula. So if you remember that, then it should be k square here. Okay? 1 by k is the, so k square here and k square here. Please correct it. Okay. 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 Now I have something in the bottom. Now this is, you take 1 by k square. Wait a minute, one second. G of, yeah, g k, 1 second. G, G 1 by, you are right. Then this should be 1 by k square, right? Yeah, that should be 1 by k square. So it should be, okay, it should be k square. Okay, I'm sorry. This should be k square. Because 1 by k is the, yeah, sorry. Yeah, yeah, this is right. Sorry. I'm extremely sorry. What I wrote was correct. I wrote was correct. It is just sigma is 1 by k. It is 1 by sigma square, so it is 1 by k square. You are right. Good. 1 by k. So it should be in the bottom. This is characteristic function. So it should be 1 by k square here. So that should come in the top. Okay. Okay. So this is what, so if you have the normal thing, this is, I'm supposed to get, yeah, this is 1 by k square. This is correct. Okay. Huh? No, this is just, I was explaining something. Okay. Now this is equal to G of G, I mean, G of GK. Wait a minute. I mean, you understand K, I mean, let me write phi. No, this is also a characteristic function with K. 1 by K, with 1 by K or K. With this is a density here now. No, now it is density, so it should be K should be up, no? K should be up. Sorry, getting too confused. This is density. This is just the convolution of the density. So K should be up. Okay. Now this is same as phi of whatever that 1 by K, whatever G of K is in the up. So this is actually characteristic function of a density with variance 1 by K, right? Correct? Okay. So this is just phi of that 1 by K whatever with x minus y there. Okay. If you don't understand, you can leave it because we have already proved the inverse mapping theorem, so that is true. It is only because I have assumed in that the f is continuous, I am proving this for a general one. Okay. So phi of 1 by k x minus y, then there is f1 y dy, whatever. Okay. But this one, phi of 1 by k x minus y, this one, there is a 2 pi, one has to be careful. But finally, you will get, I mean, there will be 1 by 2 pi coming, and let me not careful about it. Okay. You will find that constant will be there. Okay. Some constant, which will be finally 2 pi only. Okay. If you do it correctly. So this is minus infinity, infinity. So this is nothing but minus infinity to infinity e power I into x minus y. Okay, x minus y. Then e power minus, yeah, x minus y square 2k square dy. D no, wait, IXT. Okay. Then this is t square by 2, it will come in the bottom, 2k square dt, and then dy. This is just, right? This is the characteristic function evaluated at x minus y. Okay, which is some integral like this, I times x minus y t. Usually the t will come here, but since x minus y is here, I'm using x minus y here. Okay, I've interchanged the role. E of I x minus y t This is the density. Okay, because you have k on the top, it should be in the bottom here, and you have this. Yeah, that is what. Please make sure, and you get finally 1 by 2 pi here. Okay, let me not think about it. It will, if you write it in a private space, you should get the right answer. Okay, that's an exercise. Okay, the constant, you should get the right constant. Okay, yeah, it should. Okay, now it is clear. Now you take that this e power ixt is there. That you take it now, and there is an f1 y also. Okay, there is an f1 y. Now you take f1 y, then possibly you can put y minus x. X minus y doesn't matter, y minus x, because it's only square, no? It's only square, x minus y or y minus x doesn't matter, right? You have to get the right answer. I have put x minus y, but I'm changed to x minus y because this is just a square, okay? So I can put anything you want, okay? Now iyt is here and f1y is there. If you take those two terms, you get the characteristic function of this. So this will finally 1 by 2 pi integral phi and t. Okay, then we have this e power minus t square 2k square dy. That dt will dy will go with that. Sorry, dt. Okay, that's what we want. No, that's what we want. That's what we want. Yeah, what do we want? E power ixt minus ixt. It is there. E power, there is a e power minus ixt is also there. Okay. Yeah, it's there. Y minus x, no, e power ixt is also there. Okay, it should be there. Because that is the inversion formula, so it should be there. So the same way, but I should leave it as an exercise or assignment. Assignment. You do it as an assignment. Okay, because you do it with the getting the right constant and other thing. Okay, this is assignment. Even though I have already done, you can even watch the video, but get everything correctly. This is clear. This is just the convolution. This is just this claim. You have to prove one of them only. The other one is similar. Okay, you have to take the convolution. Convolution is this. Okay, then you write it as a characteristic function. Write one neatly. Okay, then you get this. Okay, this is a good exercise. I should have done it earlier, but now only it occurred to me. Okay. Okay, this is an assignment so that you can go through. Okay, now it's trivial. The whole proof is trivial. This is what I have. So now what we have is the following. We have fknx is this, fkx is this. Okay, if you take the modulus of this, okay, here n is there, modulus of this phi and t is a characteristic function, modulus 1. It has modulus 1. So this is less than or equal to some, this is also modulus 1. You have only this, right? Whatever the integrand here, okay, I don't have to write, whatever the integrand here, modulus of this is 1, because it's characteristic function. Modulus of this is 1, and you have only this if you take the modulus. This, and there is no n in that. Okay, so modulus of this is less than or equal to this function. That is integrable function. Similarly here, modulus of everything is here, it's only here, that is integrable. So you can take the limit inside. Okay, so the same, I am not writing I have said the detail. Okay, convince yourself by dominated convergence theorem, which itself we haven't proved. We are using it freely. Okay, but you will see the proof sometime in your life, which will not use this fact, so it's okay. Okay, I mean, when you having seen a proof, you are using it, you should make sure that whatever you conclude from that should not be used there. Of course, this thing will not be used there. Okay, so by dominated convergence theorem, f k n x converges to f k, no, k is there, k x, right, for all x. Okay. This is okay. Dominated convergence theorem usage, it's okay, I believe. You have a n here, but if you take modulus, the n will go away. And whatever remaining is integrable. So because of that, this is true. Okay, but this is true. But then this implies f k n, this distribution, that is whatever, I write it like this, x k n converges in distribution to this is yk. So we started with xn defined by adding a normal one, we got xkn. By adding to the x, our final aim is to prove xn converges to x. Okay. Subtract the finally, it is just we have added artificially, we will remove it. Okay. So to prove the theorem, we are just adding it because we can't prove directly. So that's why. Okay, that's what we did earlier also. For the inverse formula also, we did that. So xkn converges in distribution to yk. That is true. On the other hand, if you take yk minus x, yk is just x plus that zk. Okay, this is equal to mod of z, right? This is equal to mod of zk. Sorry, zk. Now probability of yk minus x greater than or equal to epsilon is same as probability of zk greater than or equal to epsilon. But zk is 1 by k times z, right? So this is equal to probability of z greater than or equal to k times epsilon. K times k epsilon, I mean, epsilon is fixed, k epsilon will shoot to infinity. So this goes to 0. This is just one single function. A distribution function will go to 0 as x going to infinity. This is just the tail part. The distribution, I mean, 1 minus f of fz of k epsilon. Okay. This will go to 0, right? So this goes to 0 as k going to infinity. Okay. This is fine. This is fine. This is the theorem. We started here. Yeah, okay. So I will go there. So we use this theorem, if you remember. Okay. The density converges here. So then it converges in distribution. That's what we have used here. I mean, this theorem. Density converges, then the distribution converges. We have used that. Okay. Okay. So this implies yk converges to x in probability. That's what it means. That's the statement. Okay. So which implies yk converges to x in distribution also. So we have the following: yk converges to x in distribution, xkn converges to x as n goes to infinity, as k go sorry yk, okay, as n goes to infinity, as k going to infinity. From this, we want to conclude xn goes to x in distribution. That's what you want to conclude. Okay, from this fact. Okay, so we have the following lemma, general lemma: xkn goes to yk in distribution, and yk, I mean, as n goes to infinity. Okay, yk goes to x in distribution as k going to infinity, and we also have xkn minus yk. Not, we have to bring in xn, which will give z, of course, z greater than or equal to epsilon. Okay, we have two, k and n. Okay, so lim sup in n, limit in k equals 0. Suppose here this, here everything in distribution. That's what we have proved. We have proved this converges in distribution. This converges in distribution we have already proved. These two are there. From that we want to conclude this convergence. Then xn converges to x in distribution. So these two already we have. If this condition is satisfied, then xn converges to x in distribution. Okay. So we have to see that this condition is satisfied there. Then we have to prove this lemma. So we will come to the lemma. So continuation of proof of theorem. Huh? Probability. There is no set. Yeah, sorry. Probability. Limit k, lim sup in n, then probability of this set. Okay. Even though it looks complicated, you will see that it's easy. So now we have to verify this condition. When these two happens, when this condition is satisfied, then xn converges to in x in distribution. This is the lemma. Once you assume the lemma, we will prove the theorem. Continuation of the proof of the theorem. So here, what is xkn minus x, which is equal to just zk, right? Okay. So zk greater than or equal to epsilon. This set is same as zk greater than or equal to epsilon. That is equal to z greater than or equal to k epsilon. The same thing. Okay. There is no n here. Okay. There is no n here. Lim sup of in n, there is no n here. And so lim k, lim sup in n of probability mod xkn minus x greater than or equal to epsilon. Oh, sorry. This is greater than or equal to epsilon. Equal to that. I have written, sorry. Okay, this is greater than or equal to epsilon, same as that. This is equal to that. That's what I have written. Okay. This is equal to this. Okay. And this is equal to this set is equal to this. Is it greater than this? This is equal to limit k of probability of z greater than k epsilon. Again, we have seen this is going to 0. So the condition is satisfied in our theorem. So the final conclusion is this. Okay. So by lemma, once again, lemma xn converges to xn distribution. Yeah. xkn minus x. Xkn, sorry, xn. Pardon. Sorry, this is xn. Xn. Xkn defined as xn plus zk, right? So this is xn. Sorry. If I have written proper notes and copied, everything will be correct. But I don't do that. Unfortunately, I don't write notes. Okay. You can write notes and put it in Google Drive, and I can give a link that will be a practice for you. Okay. So now this is clear. Xkn minus xn. Okay, it should be xn. Okay, that is equal to zk. There is no n here. So lim sup is, there is no point in lim sup. Limit only, that goes to 0, which we have already seen. Okay, this goes to 0. So xn converges to xn distribution. So we only have to prove this lemma. The lemma says the following: xkn converges to yk something, and yk converges to x. These are all happening in distribution. Then this condition is satisfied. When this condition is satisfied, this is very similar to what we have proved. This, you can see that this is very similar to convergence in probability, something to do with that, similar to that. So we will, from here we want to go there, means we will use the same idea what we have used. I mean, condition in probability implies condition in distribution. We use an idea, no? The same idea we will use. We want to prove proof of lemma. Okay. Maybe here I will write it xkn converges to yk in distribution, and yk converges to x in distribution. Then that limit, whatever limit k, lim sup n of that that is 0. Okay. Okay. Now we want to prove. Then we want to prove this, right? We want to prove xn converges to x in probability. Yeah, sorry, distribution. So we want to consider this probability of xn less than or equal to x. That is what is fn x is. We want to consider this, right? Okay. As before, the same thing, it's an exercise. As before, this is less than or equal to probability of x less than or equal to x plus epsilon. Then probability of mod x minus xn. If you remember, this is the first proposition we proved, greater than or equal to x. You, well, Shall I go through this? This is clear. The same proof. Okay, same thing. Similarly, probability of x less than or equal to x minus epsilon is less than or equal to probability of xn less than epsilon plus probability of x minus xn greater than or equal to epsilon. Same thing. Okay, so we put this in the middle, which is fn x. Okay, this in the middle is greater than or equal, less than. I'm sorry, there is something. No, not xn. I can change to anything, right? This can be x and kn. Sorry, I can change to anything I want. I mean, this there is no x or y or anything here. You can take any random variable and write this inequality. This is for any random variable. Okay, so I said x, but let me use this. Okay, xkn. Okay, then here also xkn. So this is xn. This is right. Then xkn minus xn. This is okay. When in the earlier thing, whatever I had, this is xn. This is equal to xn less than or equal to x. Then xkn greater than or equal to less than this, greater than this. Okay. So you write it like this, you get this. Okay, exercise. The same thing we have done. Okay, is okay. So this thing says that this is this term. This is which term? This term. Fkn, not this term. This term. Sorry. Fn at x, that is this term, is less than or equal to this, which is Fkn x plus epsilon. Okay, minus that probability plus that probability of xkn minus xn greater than or equal to epsilon. Okay, which is less than or equal to, we have this here and we can bring it here. So which is Fkn x minus epsilon minus probability of the same thing, xkn minus xn less than greater than or equal to epsilon. Okay, so kn is here, kn is here. Okay, now we have fnx in the middle. There is no k here and there. Okay, there is no k in the middle, k in the middle. So you can take lim inf and lim sup here in n. Okay, but then this converges this. I mean, no, this does not go to 0. You have to take first lim inf in n, lim sup in n. Huh? No, this is something less than this. So lim sup of this will be less than this, right? Okay. So you can take the lim sup of this. You have a lim sup here. Okay. Okay, you can take lim. Yeah, negative. So you can take the, yeah, right. Lim sup here, it should be lim sup here. I mean, it should be, sorry, if you take lim inf here, if you take lim sup here, that is less than this. Lim inf will be greater than this. Okay, so that's what we want. Okay, let me write it. Yeah, good. Okay, this says that lim inf of whatever fkn is less than or equal to limit. This is limit. This has limit. Okay, fkn in n. Okay, of x plus epsilon. Okay, plus probability of mod of xk. There is a, if this continuous variable, it will be easy. Let's see. So there is a lim sup here. Okay, lim sup is less than or equal to lim sup of the same thing, Fkn, okay, that is less than or, I mean, lim sup is okay. This is less than or equal to this. This is less than or equal to that. That's okay. What I have written. Lim inf is less than lim sup of anything. Okay, that is less than or equal to that side. Okay. Now this whole thing is greater than or equal to whatever I write here. What I have here, first one. What is first one? Which is limit of Fkn x minus epsilon. Then minus again here lim sup, right? Lim sup of the same thing. Probability of xkn minus xn greater than or equal to epsilon, whatever. Okay. 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 Now we have to take limit in this. This is in lim sup in yan. Okay. This is in yan. So I mean this x minus epsilon, this Fkn will converge to the yk, right? We have x and k converges to yk. Okay. So this will converge to the distribution of yk. And yk will converge to x. But you may be worried about the points of continuity or something, but there is a the discontinuities are countable for this function f. So you can have epsilon nice enough so that this is, I mean, okay, you can take a limit if you want, okay, where epsilon n going to 0 or something, so that they are all continuous there, which is possible. So let's not go into the detail, okay, because it's continuous. Points of discontinuity is countable for this distribution function, which is right continuous, right? You know, any increasing function has countably many discontinuities. So that's not a problem. Okay, less than this. Okay. Now, if you take oh no, where is this k coming? There is no k here. I'm sorry. I'm using this inequality. You have to take lim sup lim inf of this only. Sorry, lim sup of this in n, this in n. Okay, there is no k in this middle. Okay, I hope if you look at the video, it will be clear. Okay, so I have this inequality. Okay, in this inequality, Fn is in the middle. So I am taking lim inf and lim sup of this, which is in the middle like this. Then that is greater than this. That is greater than this. Okay, lim inf is less than lim sup, and you can take the lim inf of that, which is this limit here, which is lim sup here, minus here. So lim sup of this. Okay. Okay. Now if you take limit k now, okay, limit k will give you, I mean, we have x and k converges to this. Why? You should get f here, right? If you take limit k here, taking limit k going to infinity, this will be 0 by the assumption. We have the assumption that this is 0, that is 0. Okay. Finally, we only have f of x minus epsilon is less than or equal to limit of fn x less than or equal to f of x plus epsilon. Is that right? We have lim inf less than or equal to lim sup, whatever we have here. Okay. So that is less than or equal to this. Now you take the limit over k. Okay. Limit over n will be fk. But if you take limit over k, that will be that f. That is what our assumption is, right? X and k converges to this, yk converges to this. F is the distribution of x. Okay. If you want, you put x here. But that's what I said. I will use f and fn freely. Okay. This is the distribution of that. So we got this. That's what we want to prove. By now take epsilon going to 0. If x is a continuous point, the same proof. X going to 0, then the limit will be equal to that. That's all. If you want, I will give you what we did. Overview of this. Do you want it? Okay, let's start from 0, what we did. Where is the proof of the, where is the theorem written? Ah, theorem is here. Okay, this is the idea. Even if you don't understand here, you should be able to write it and prove it. Okay, once the idea is there. Okay, the theorem is the following: xn's are random variables. Xn, we assume that xn's are random variables. We assume the following: the characteristic function converges. Phi and t converges to phi t. Then we want to prove the random variable converges in distribution. So the distribution function converges at all continuous points. That's what we want to prove. For that, what we take first, what we do is we make it double index. We have xn. We want to prove xn. We have the characteristic function converges. We want to prove xn converges to x. So we add normal random variable to that. So xn, this is xn. Okay. So we make double index, a double sequence, xkn equal to xn plus zk. Similarly, we take yk equal to x plus zk. Okay. Then we compute its density using some formula which I went through something. So that is what this computation is, proof of the computation. Okay. But then once you know that, then by dominated convergence theorem, we know this density converges to this. Because the density converges to this, the distribution will converge. That we have proved. Okay. It's only the distribution convergence does not imply density convergence. Density converges, distribution converges. So we have proved from the density we have distribution converges. But for this yk, we proved it's very easy to see that because the difference is just a normal random variable, we see that it converges in probability. But we have proved convergence in probability same as convergence in distribution. Okay. So we have xkn converges to yk, and yk converges to the required random variable in distribution. Okay. But then we have to somehow connect. There is no xn here. We have to connect something. That connection, sorry, the video is not there, unfortunately. So I can't go through it again. Okay. I said all that, but the camera was pointing here. That's okay. I'm sorry. But you can look at it. Okay. So now we don't have, there is no xn there. So for that, we use the following lemma, which is here, which connects all these things. Xkn converges to yk, that's what we have. And yk converges to x, we have. But then xk and xn are connected by this. When that is the case, xn converges to x. That is the theorem. That is the lemma. Then we verify that condition. But that condition verification is just very easy because this is just again a normal greater than the same idea works, which is greater than, which goes to 0, which is just the, which is very direct. Okay, there is it's the same as that. Okay. Now we have to prove the lemma. This proof is same. The idea is same as what we used when convergence and probability implies convergence in distribution. We use some inequality. Same inequality is used here. Okay, except that we take a lim sup and lim bib, same inequality. We use the same inequality and we get that. And finally, we take, but here we have to take, because it's a double index, we have to take a lim sup and then a limit. Two things we have to take, and then we get the answer. Okay, as far as I know, every detail is written here. Okay, maybe a bit messy, but if you look carefully, it's all written here. Okay, I'll stop here.